good morning, good evening, good afternoon, everyone, depending on where you are. So welcome to our combustion webinar again. Today, it's my great pleasure to introduce you Professor Zhuyin from Tsinghua University. He will give us a talk about transported PDF simulation of turbulent flame with uncertainty quantification UQ. So give you a little bit introduction about Professor Ren. Professor Ren received his PhD in mechanical engineering from Kernel University in 2006, which I think worked with Professor Stephen Pope. He has been a professor of the Center for Combustion Energy at Tsinghua University since 2013. Prior to that, he was fluid specialist at ANSYS Fluent and mechanical engineer at the GE Global Research Center and an assistant professor at the University of Connecticut. His research interests including turbulent combustion modeling and high-fidelity simulation with detailed chemistry. Dr. Ren received the Bernard Lewis Fellowship from the Combustion Institute in 2008 and now serve on the editorial board of Combustion Theory and Modeling and the Journal for Propulsion and Power. So regarding the transport PDF for modeling, I think Professor Ren is one of the very few leaders in the world, and he also published a very top-cited review paper on that. Many of you probably read it before, and especially in China, he's definitely the leader of turbulent combustion modeling and simulation. So let's listen to his wonderful talk now.
Right? Could I just add something?
Professor please. Yeah, please.
Graduate from Cornell, and his academic record during his PhD work was break all the records. Okay, at Cornell, it was just incredible. And Professor Steve Pope always brag about it. Not brag, just mention about it. So it's just he is a really phenomenal person, and just great pleasure to have him here. All right, Zhuyin. That's it.
So yeah, thanks and Professor Yang and Professor Law and also Professor Sun and Professor Yu and also the combustion webinar organizers and I really appreciate your efforts and telling me and giving me this opportunity to introduce our recent progress and in transport PDF simulations. So my talk will cover and some aspect of the transport PDF method, fundamental stuff, and also I will introduce our recent work on zone adaptive modeling and based on transport PDF method, as well as some mixing model development and for reactive scalars in terms of the evaluation mixing format, as well as hybrid mixing timescale models we proposed several years back. And in the last, I will introduce the uncertainty quantification and for turbulent frames using the method called active subspace. Okay, and we know for practical combustion devices, it very often has a very complex geometry, and it evolves and multi-scale, multi-physics such as droplet and evaporation and breakup, and radiation, turbulent mixing, and chemical reaction, etc. Okay, and with the ever increasing and requirement for emission, as well as a strive for high thermal efficiency, nowadays turbulent combustion has pushing towards the near and the thermochemical conditions. So very often, and we will see in a practical and a combustor, you will have a mixed mode of combustion process such as autoignition and premix, non-premix, and also very often you will run into near limit phenomena such as local extinction, reignition, etc. Okay, and in all these complexes and phenomena, it evolve under the highly nonlinear and strong coupling between the mixing and the chemical reactions, okay, for which it is quite challenging to model. So over the past 30 years, and with the development in computers and numerical algorithm as well as turbulent combustion models, we see a big advancement in numerical simulation of flames. For example, back in 90s we can do 2D simulations of laminar flames. And nowadays, we can do larger simulations both for the laboratory flames as well as the practical and combustion devices like the aero engine combustors. And back in 2014, for computational for the revolutionary computational and aero sciences, okay, the so-called CFD Vision 2030 project. And people actually lay out quite a comprehensive roadmap for high fidelity and aerospace and simulations. So it lay out the modeling as well as an algorithm development needs and in the various areas. So within the physical modeling area, and what we can see is the use of a realistic chemistry and is a larger simulation of turbulent flames is one need, okay? And also in algorithm aspect, and the uncertainty quantification is also quite an urgent and acute development need. So in the following, I will describe to you our recent progress we made and in these two areas, and specifically the use of detailed chemistry as well as UQ and in the context of transport PDF method. Now, we know for turbulent flames, it involves a wide range of length scales as well as chemical time scales. So very often for practical and combustion devices, one cannot resolve all the length and chemical timing scales in turbulent flames and by the so-called direct numerical simulations. And this is just computational too expensive. So very often, for practical and combustion devices, one use the statistical models like LOANS or LES approach. And in both these two approach, only the integral length scale or the large scales are resolved, while the small scales and like small eddies and sometimes the small flame features are not resolved, okay, and which are need to be modeled. And one thing I want to emphasize here is, unlike the non-reacting flows, okay, and in which the small scale motions like the small eddies are dominant by the large scale motions. And in that scenario, actually, the modeling for the non-resolved and small scale and the phenomena are pretty straightforward. And for turbulent reacting flows, and unfortunately, the most important heat release and the process and occurring at these very fine flame structures, and which are not resolved and which should be properly accounted for in turbulent combustion modeling. So because of the the small scales are not being resolved, we run into this big challenge in terms of modeling and the mean reaction short term. So one well-known issue we have is that, and if we look at the speed transport equation and in the LOANS and LES context, and the mean reaction rate and cannot be accurately computed by using the mean and the resolved mean temperature or mean mass fraction of species. Okay, and the effect of turbulent fluctuations on chemical reaction rate must be somehow accounted for. So actually, back in 2012, during his hotel lecture by Steve Pope, he laid out the progress we made in turbulent combustion modeling. So back in early 80s, due to the limitation and the computing resources, and also in the modeling development, and very often we use the LOANS and plus and framelet approach. And then we move into two directions. One is resolving more turbulence, and one is resolving more chemistry. and with the development and of computational resources as algorithm, etc., and in early 20s and like 2005, and we all converge towards and larger simulation and plus and certain and fine models like transport PDF. Okay, so since 2012, and actually we see and some very recent development in the combustion modeling, the so-called and active combustion modeling, and pioneered by the Stanford group, Matthias group, and also we see some representative work by the Yukon group, as well as Reese and the group, and with using the combination of transport PDF plus and the framelet approach. Okay, so no matter what, and in terms of combustion modeling and the transport PDF and like model, and we don't assume the existence of low dimension manifold, and also and in transport PDF method, and the mean reaction rate is is treated exactly and without any modeling. So in that regard, and the transport PDF modeling with detailed chemistry or realistic chemistry has advantage and in terms of resolving the near limit phenomena. So in the next, I will briefly and review some fundamentals of transport PDF method. Then I will describe our recent work in the zone adaptive modeling based on transport PDF method. Now let's assume we are considering the 1.1 time PDF, joint PDF of compositions. So what you see here is the the governing equation for the joint PDF and the joint PDF composition that consists of enthalpy and species and mass fraction. So in this transport equation, you'll notice that the chemical reaction source term is in a closed form. And because we only use a 1.1 time PDF and we don't have any gradient information, so the term which represent a micromixing essentially is a market diffusion effect and need to be modeled. Okay. So the first success we see in the application of transport PDF method is date back to 2000, around 2000. And pioneered by a group at Cornell as well as Imperial College by Professor Peter Lindstedt. Okay, and in that application, what they have demonstrated is that for this really challenging and Sandia flame DEF series, and by using the transport PDF method, you can well represent the local extinction effect. Okay, local extinction and reignition and okay, so that's the fundamentals of the transport PDF method. And due to the high dimensionality and is an independent variable. So if you look at this governing equation, if you direct solve this transport equation, use a finite volume method, and the number independent variable is pretty high. So in reality, and very often, we use a particle mesh solution method. Okay, so essentially, you use a Monte Carlo method to represent the joint PDF. So in the simulations, and very often you will release a whole bunch of computational particles, and each particle represents one puzzle of gases and fluids. Okay, and these particles will evolve in the computing domain and following the velocity field, and these particles will interact with each other and by exchanging mass and energy, and essentially represents a micromixing process. And also, these particles will react and essentially go through the homogeneous reaction process. Okay, so as I illustrated here and in this animation. So what we can see is in this particle mesh and solution method essentially. And the lines or LES provide the PDF solver with resolved mean velocity and the field velocity, etc. And the PDF solver will feed back to the LES solver and with the density as well as sometimes the reaction source information. Okay, so back in 1998, and GV, provide payment GV and POP and etc. And say for the first time and demonstrate and the use of LES FDF for and reacting and solutions. Now since then, and we see a whole bunch of and propagations in LES FDF or LES PDF. So here I briefly summarize and all the progress were made and back and from 2009 and 2019. Okay, so you will see and more people got into this business, and actually. And in terms of the computational platform, and actually for transfer PDM method, and over the past years, and we see both the block structure mesh and computational platform as MGA and HPDF approach, and also we see and the unstructured and commercial unstructured as well as a commercial platform like the ANSYS Fluent. So it does have the transfer PDF and and also people and coupled and the transfer PDM method and within the open form and open source and okay, and also people have demonstrated the use of transfer PDF for both the laboratory frames as well as the practical and combustion applications. And as I mentioned earlier, and the first successful application of transfer PDF is for non-premix frames, okay, and like the Sandia DF series. And nowadays, and the application of transfer PDF have been extended to premix frames, partial premix frame, as we recently demonstrated for the thinning parallel premix jet frames, and we obtained a very good agreement with experimental data. And also Hang et al. And say extend the transfer PDF and to the simulating the shooting flames, and also recently we extended to simulating and the dilute ethanol and the spray frame. And very interesting, and what you see on this plot is with with the advancement if you use more and more sophisticated and turbulence-chemistry and interaction closure, like if you move from the characteristic timescale models and to use the lambda family model EDC and to the most sophisticated transport PDM model, you will see the agreement and with experimental data and get a dramatically improved. So as I mentioned earlier, and the transfer PDM method does has advantage in resolving and the intense one TCI. Okay. So that's kind of the progress we have made and for transfer PDM method. And very often, and transfer PDM method is get criticized, and because of its high computational cost. And since you need to introduce a whole bunch of Monte Carlo particles to represent this PDF, and in general, and the transfer PDM method is kind of at least twice expensive as the lambda family model. Okay. So the question to ask ourselves is how to balance the computer cost and the model accuracy for practical simulations. So the one approach we come up with and I actually follow the work by Rice, okay, and it's a zone adaptive combustion model approach. So in this approach, what we did is we spatially assign heterogeneous submodels, okay, and that is dynamically determined by the local and the flow and the flame characteristics. So now let me spend a few words on how we achieve that. Okay. So in this framework, and actually we developed this framework and in unstructured and open source code. And here I using this simple jet frame as example. So what we do is we use and throughout the whole computer domain. And we use a simple combustion model like the EBO model and with a simple mechanism, okay, and it is solved through the whole computer domain, okay. Only in the regions and you have an intense and chemistry interaction, and we will assign this and transfer PDL model with a realistic or detailed mechanism, okay. So essentially, and throughout the computer domain, you will have two sets of combined models, one simple model with simple chemistry, one advanced model, transfer PDF model with a detailed chemistry. Okay, and the PDF zones, okay, can be dynamic and assigned and based on the local and flow and flame and the characteristics. So what I illustrated here is essentially and the dynamic change of and the PDF region, okay, in these 2D simulations. So in terms of the coupling and between the sub-models in this adaptive approach, so what we do is we use a base model, okay, and to solve the whole domain, okay, and this base model will provide and as high fidelity and PDF region, right, and with necessary and boundary conditions like and the mass flow rate, etc. Okay, so those are buffer region. Okay, and then the advanced model and essentially here is a TPDF model, and will provide and the mean reaction source term and as well as a relaxation term. Okay, and back to the base model, so that and in the PDF region, since you have duplicated informations, right, and this information should be consistent. Now let me give you a quick illustration and what we can achieve with this and adaptive modern approach. So what you see here is a really simple and turbulent hydrogen and diffusion flame, okay? And this is the domain looks like, and this is essentially the contour of temperature, okay? And computed by the standalone PDF, or that means the whole region are computed by the transfer PDF method, okay? So this is kind of computationally expensive. Now, with adaptive region, with adaptive and modeling approach, and what you will see is only along this high intense reaction region, okay, where we assign this transfer method, and in the blue region, and since there's essentially no reaction activity, and essentially we will use this and one step and laminar fan rate model, okay, and essentially you don't have any computed particles, okay. So what I'm showing here is essentially a comparison and between the different and modern approaches. So you will see three results here, and the lambda fan rate model is essentially and the prediction with this model with a one step and a mechanism. Okay, so this is blue curves. Okay, and the TPDF is essentially and the standalone PDF method. Okay, essentially you solve and the problem with using the transfer PDF for the whole computing domain. Okay, so adaptive and approach is essentially only in the highly and intense reaction region. You use transfer PDF. Otherwise, and for the remaining regions, you use the laminar fan rate model. Okay, with simple chemistry. So key message and you see here is okay. With this adaptive and zone modern approach, and its accuracy, okay, its accuracy could maintain and the same accuracy with the standalone transfer PDF method. So the accuracy is preserved, okay. And also we examine and the convergence characteristic of this and zone adaptive modern approach. And what we found out is okay, so IMSL decay as and the number of particles, okay. Essentially it's the same as the standalone PDF method. And more importantly, and compare with the standalone transfer PDF method, and for this really simple problem, and we can achieve a computational speed of about 2.1 and for the whole simulation. Okay, so that means, and with this adaptive modern approach, we can maintain and the high accuracy of the standalone transfer PDF model, but at the same time, and we can greatly speed up the computational cost. Okay. So that's and the progress and we made and in terms of for the transfer PDF method in terms of how to accelerate the calculation. Okay, and by using the zone adaptive modeling. And another key ingredient actually very often. And the transfer PDF method is get criticized or get doubted is its modeling for the micromixing process. Okay, so now and in the next few slides, I'm going to introduce what we have done and for the micromixing models. So as I mentioned, and since we very often consider the 1.1 time PDF, and we don't have the gradient information, right? So the market diffusion has to be modeled. So what a micromixing model does is describe and continuous diffusion rate, and a typical micromixing model, and can be cast and in the following general form. So essentially, and the evolution of particle composition and due to market diffusion, and it can be represented and by these two pieces of information. One is a mixing format. So essentially, and within a computer cell, and you have a bunch of computer particles, and how a particular particle is going to interact with the surrounding particles. So this is governed by the mixing format. Okay, so the second ingredient in a mixing model is essentially and how fast you are going to exchange the information, mass and energy with the surrounding and particles. Okay, so this is governed by the tau. Here is essentially describing the scalar mixing time scales. So over the past and years, and people have come up with a whole bunch of mixing models. And here I only list a few, okay? And these are the ones and available in the commercial software like ANSYS Fluent. Okay, so the first one is IEM. So essentially, and within a CFD cell, and a particular particle will evolve its composition towards the ensemble mean, essentially the mean, okay? And the second one is a monocolor, modified curl and method. So what it does is randomly select the pairs of particles within this computer cell, and then you will randomly exchange the mass and energy. Okay, and the third one is the EMST, and the reason being why it is developed is people gradually realize and actually during the mixing process, it's very important to maintain the interaction and the local in composition. Means that and in a given CFD cell, if you have two particles that is too far away from each other in composition space, they should not interact with each other. This is actually true in the limit of flamelet. Since in each CFD cells, you can have both the burned and unburned particles and sitting on the different side of the flame. And if you direct and mix this to each other, actually it's physically not true, and it's a limit of flamelet. Okay, so EMST and essentially what it does is reconstruct so-called Euclidean minimum span tree in the computing space, and a particle will only interact with its neighboring particles or by exchange as. So the first thing we did is we evaluate on how important to maintain a localness when we consider mixing. Okay, so we consider this and the DNS of data of the temporal evolving and premixed hydrogen air slot flame. So essentially, and in this DNS flame, and the flame is propagating to, from the outside towards the center. Okay, so what you see here is the temperature contours as a different time instance. Okay, and here we consider two cases and both in the same reaction zone regime. As the DNS is performed by Hawks and back in 2012. So what we did here is we performed the length and transfer simulation and in conjunction with DNS. So what we do is we perform this 1D flame calculation, and the transfer PDF particles are evolving by the position following this equation and the composition and following this equation. Okay, so unique thing in this type of simulation is we can extract all the needed information from the DNS data So we can suppress the velocity and all this and the turbulent diffusivity, etc., and also the reaction short term, okay, from the DNS. Okay, so during this calculation, we can isolate and the errors. So only errors are obtained and in the mixing format and the term. Okay, and even for the mixing time scale, we can extract from the DNS data. Okay. Now this is what we see and for this and premix flame. So what we see is for both these two flames, okay, and the right line is and the DNS data. So this is the profiles of temperature at different time instant, okay, and you will see as a prediction from the IEM is far and off from the true DNS data, and for both these two cases, okay, and only EMST can capture the mean and RMS temperature field relatively well, okay. So from this study, what we see is, okay, for premix flame as well, and the localness in composition is very important and to get an accurate prediction of the flame evolution. Now, one thing we did more is, okay, and for EMST mixing model, actually it is quite time consuming to construct and the Euclidean minimum span tree in the computing space. So the computing cost is quite actually and relatively large. So one thing and we think in our mind is it possible we can come up with a simple model, okay, and which can maintain and the localness in composition, but at the same time and we can cut down the computation cost. So this is what we recently come up with, so-called kernel constrainer mixing model. Okay, the model is essentially based on some modified mixing model. Okay, the unique feature we introduce and in this model is, okay, when we select the pairs or particles for mixing, we attach a kernel function for each and the individual particles, okay, and only the two particles and within the kernel size, okay, they can be mixed, okay. So essentially, and we set a specified threshold value, and essentially by and only within set and the threshold value, and the two particles can mix with each other. So the localness is constrained actually is introduced by this kernel size, okay. And later on we will see and this model and can relax to modify curl or EMST, okay, and depend on how you vary or model and the kernel size. If we do a quick comparison and about the model performance and for the existing ones like IEM, modifier curl, EMST, MMC, and introduced by Klemenko, and SPMM and introduced by Steve Pope and back in 2013, and our kernel and constraint mixing model actually and have all these properties and actually particularly the computational cost and in terms of how it scale with the number of particles in the cell is OMP, okay. So this is dramatically and come down and compared to the EMX mixing model. We did some preliminary testing and for this new mixing model, and what we found out is for both the inert mixing and actually this 2-point mixing and against the DNS data and our kernel model and can well reconstruct the evolution of the PDFs or Fs, okay, and as a different time instance, okay, and also we did a comparison and in the ethylene and airframes against the DNS data, and what you see here and is one and the scatter plot at one time instance, okay. So here is the DNS data, and what you see here and is a kernel mixing model and with a specification of different kernel size. And one thing you see is this model can well represent DNS data, and also depend on how you specified and how you model the kernel size it can, degenerate to the modified Kerr model or degenerate and to the EMST mixing model. So the key message here is we have one model and the kernel mixing model, and which can represent the localness. So in the future, what we'll do is we will come up with a model and for the kernel size. So we hope and in the future, and the kernel size will dynamically determined by the local and flame and flow characteristics instead of manually specified by the user. So that's kind of the progress we made for the mixing format. And another ingredient, as I mentioned earlier, is a mixing time scale, right? So for turbulent frames, and very often, and one assume and the scalar mixing rate is proportional to the turbulent time scale, as I showing here, right? Tau mix is scalar mixing time, and tau t is turbulent mixing time, okay? And this is quite true actually, and for turbulent non-premix frame in the lens context. And also people see and this and the ratio is in order of 1 and for passive scalars such as okay. So this conventional and mechanical to scalar and mixing time ratio model works okay and for turbulent non-premix frame. But when it comes down to turbulent premix frame, okay, and the story is a little bit different, okay. And we know, and in a turbulent premix frame, and the local gradient is not only affected by turbulence, okay, and it is also controlled by the flame flow, okay. So essentially controlled by chemical reactions. So in terms of turbulent premix frame, and the mixing time scale is no longer, it's not only a function of the turbulent time scale, and it will also depend on chemical reactions, essentially the flame structure. So one thing we look at is okay, and we look at as a scatter plot at some representative and DNS data sets. So what we see here is we consider two cases of this premix flame. So this actually Starr-Benson flames, okay, at a different Doppler number, okay, and so the case A is close to a flamelet regime, and the case C is close to a broken reaction zone regime, okay. And what we did is we show the scatter plot of the radicals, okay, plot them against the progress variable. So as you can see here, and even for the case near close to the broken reaction zone regime, and the scatter plot are still scattered around certain laminar flamelets. Okay, so inspired by this observation, and one thing comes to our mind is okay, maybe we can model the framing induced scalar dissipation by introducing a reference frame. So we can introduce a reference frame, essentially the lambda frames, okay? And then the contribution or the flame induced scalar dissipation can be modeled by taking this reference frame and multiply essentially the PDF of the progress variable, okay? One nice thing about the transfer PDF method is okay. Once you know the reference frame and the PDF of the progress variable itself is available in the solution. Since we solve a whole bunch of particles, and those particles represent this PDF distribution. Okay, so in the context of transfer PDF method, and the flame induced scalar dissipation can be modeled once we have a reference flame structure. Now, and once we know how to model the flame induced mixing, and we come up with a hybrid mixing time scale by using this formula. Okay, so essentially in a turbulent reacting flows, and for the reactive scalar, and we consider its mixing governed by these two processes. Okay, so turbulence part, and this is a conventional and mechanical to scalar ratio model, and the second part is a flame induced and contribution. and we quantified and the relative contribution by this segregation factor. So essentially, this is a normalized and a progress variable valence. Okay, and in the frame region, and we know and the variance and is large and is actually approaching to 1. So this model will degenerate back and to the one that is and the gradient is 100% governing by and the frame. Okay, and if it is in the broken region zone regime, and the variance will be small, and eta and essentially will approach 0. So in the broken region regime, and the model we degenerate back to and the conventional and mechanism to scalar and time scale ratio model. Okay, so as you can see, and this model and the hybrid mixing time scale model, and at least can model and these two extremes look correct. And back in 2017, and we did some and a primary assessment and of this model in this and temporal evolving and premix hydrogen air star jet flame. Okay, so one we see before. And this is the DNS data, and you construct DNS data, and this is the hybrid model. And as you can see for both and these two cases, okay, and one near broken reaction zone regime, and one kind of is more and frame regime. And for both cases, okay, and as a hybrid model will reproduce and the DNS data. Okay, so actually, and with this and hybrid model, we can do more things. Okay, now since we introduce and the reference frame and for the frame induced and the dissipation rate or mixing time scale, and actually the mixing time scales for species are different. Okay, so by using the hybrid model, and we can model and actually differential diffusion in different frames, and that will be important these days when we consider hydrogen economy, right, and hydrogen frames. So here, what I show here is actually a DNS of turbulent premix methane air burns flame. Within even for this frame, okay, and based on the DNS data, you will see and dramatic different mixing time scales and among the species. Okay, and the difference could be up to a factor of 10. Okay, now let's see and how this hybrid mixing model perform. Okay, how well it can model analysis and differential diffusion. So this is what we do, and with this hybrid timescale model, and we can model and the diffuse species and mixing timescale, and by using this formula. Okay, and what we do here is we do a prior test and to compute and the ratio of the progress variable and the mixing time and individual species. Okay, and what you see here is this is a CO of C2, so it's a mixed time scale ratio between CO and O2, and the black dot line is a DNS data, and this is a prediction from our hybrid time scale model. Okay, and this is for case A case, and this is for case C. Okay, as you can see, and for both scenarios, and this hybrid model can will and represent and or models differential mixing time scales for species. And most recently, and what we demonstrate actually is that actually and the differential diffusion is quite important and for predicting and the suit. Okay, so this is what Zhou and Effort and what they did and in the PCI paper. So the DNS data set considered here is a temporal evolving non-premix ethylene flame, and also you extract a mean from turbulent diffusivity and species mixing frequency from DNS to fit the Luan's and TPF simulation. And what you see here is okay, if we use IEM model, modified Kernel model without differential diffusion, and this is the DNS data and this is the prediction. Okay, and if you consider and the differential diffusion of gaseous species, and now you can dramatically improve the prediction for the suit. Okay, so that's and demonstrated and the importance of differential diffusion for suit prediction, and also demonstrated and the accuracy in our hybrid timescale model for model and differential diffusion. Okay, so that's and the progress we made and for mixing model and for the next and 10 minutes, I will briefly go over what we did for UQ and UQ in terms of PDF simulations. Now, as we know, and in nowadays, and why computational simulation can be applied to complex system, right? And it's hard to quantify the accuracy and of the CFD results. And in the CFD simulations, and you have errors coming from some model assumptions, and you have the errors or uncertainties in the simulation inputs, and also you may have errors in numerical resolution, such as finite number of grid. Okay. So one thing and a particular thing we want to address here is how to quantify, okay, and the impact of the impact of the input uncertainty on the predictions. So essentially, we need to propagate and the uncertainties in the properties, model parameters, or the boundary conditions, and the final results. So for the uncertainties in CFD, actually, and once you know and the uncertainty parameter and the PDF distributions, actually the task is pretty straightforward. What you can do is, okay, you can draw a whole bunch of samples in this and high dimensional and input parameter. For example, it could be kinetic parameters and turbulent model constants, and also boundary conditions. Okay, so for each individual samples, you can run a CFD calculation. You get one prediction. Okay, by performing manual and CFD calculations, you get the PDF. For example, in this case, and frame speed. Okay, so this so-called direct and Monte Carlo and sampling approach is very straightforward. And the problem here we have is, okay, for turbulent combustion simulations, okay, the parameters and the number of parameters, okay, and with uncertainty could be very high. For example, if we use a detailed chemistry and the rate constants in the individual reactions could be many, right? And also you could have turbulence model parameters and combustion model parameters as well as boundary conditions. Okay, so the dimension of the parameter is high. Okay, so you need to draw many samples. So that's one challenge. And even worse, okay, and we know for each individual CFD simulation, it's already quite time consuming. So it's almost impossible for you to compute many CFD simulations to get this PDF. So for UQ and in CFD, we need to do two things. One is how to reduce the number of uncertain parameters. Okay, so it's here, and we need to essentially use the dimension dashing approach. Okay, the second thing is essentially how to employ a separate model to speed up and the individual CFD calculations. Okay, so in the following and particularly I will introduce a particular method called active subspace and for dimension reduction. Okay, here is some fundamentals about the active subspace. So active subspace method is a dimension reduction technique and proposed and developed by Constantine actually around 2014 or 2015. Okay, and the unique feature of AS is it detects subtractions of the strongest variability using evaluation of the gradient and subsequently explores this direction to construct a response surface on a low dimension subspace. Okay, and later on I will explain what does this mean. Okay, and one thing we notice is active subspace recently has attracted many attentions in many fields, such as combustion simulations, as what we did for the camera frame, and also for the airfoil shape parameterization, and also in the turbine blade and optimization, as well as the flow around the cylinder. Now, the key mathematics and basis for active subspace method is as following. Okay, suppose you know the input parameter. Okay, this is parameters with uncertainty. and let's denote it as x, okay? And for each and individual parameter, you know the PDF distribution of this uncertain parameter, okay? Now, and let's consider output. And essentially, this is the object of interest, okay? And this called B, and frame lift-off height, etc. Okay. So what is the subspace the active subspace method does is okay. It will construct this and matrix of covariance of gradient. Okay. So here is a gradient of the object function with respect to x. Okay. And pi here is a joint PDF of these uncertain parameters. Okay. So once you get an estimate of the covariant matrix, okay, what you do is you perform a singular value decomposition, okay, and the singular values or the eigenvalues, okay, and represents the significance, okay, and also the factors, the leading factors, okay, and represents the directions and in which the object function will vary the most, okay. So this is essentially the key and mathematics about the active subspace, and in contrast to the sensitivity analysis we very often see. Okay, the difference here is okay, in the sensitivity analysis method, and the subspace is actually the subset of an xi as a basis, and whereas in the active subspace, and here it is a linear combination of xi as a basis. So with active subspace, and you can greatly reduce the dimensionality. Okay. Let me use this function as example. Okay. So in this exponential function, you have two input parameters, x1, x2. Suppose they are has certain uncertainty. Okay. And what you see here is a contour, right? And of this function, right? And what you notice is okay, only in this direction, right? And the solution varies the most, and the solution essentially remain constant along this in active and subspace in active direction, right? So essentially, what active subspace can do for you is it will identify and this active direction, okay, in which and the solution vary most, okay. So what I will demonstrate is okay, by using the active subspace method, and we can gradually reduce the number of the uncertain variables, okay. And also, and I will briefly describe how we can propagate the kinetic physical uncertainty in frame simulations. So as a start, and what we demonstrated back in 2018 is okay. Let's demonstrate this for the autoignition process, okay. So we consider hydrogen, methane, and other fuels, okay. And the quantity of interest we consider here. So F here is ignition delay time, for example, and the input with uncertainty as also rate constant, okay. And we prescribe, we specify this log normal distribution for this rate constant. So you have a certain uncertainty, and the uncertainty factor is taken from the literature. And what you see here is okay. And this is essentially the distribution of the eigenvalues of the covariance matrix. And what you'll notice is, and for hydrogen flame, you only have one leading and eigenvalue and one leading and active direction. Okay, and also we notice is okay for this leading active direction, and actually it's a combination of these two elementary reactions. Okay, so this is R9 and R16, okay, these two reactions, okay. And also what we see here is okay, by only consider the change in these active directions, okay, and you can very well represent and the distribution of the ignition delay time, okay. So essentially, all the data are collapsed to and along this one-dimensional curve. So that's what we did, and for the 0D autoignition case, then we extend this method to propagate the kinetic uncertainty in this hydrogen and autoigniting and flame, this so-called capital flame. So the quantity of interest we consider here is the lift of height, okay, denoted as H. Okay, and one thing we did here is things and constructing the covariant matrix by running and manual CFD simulation is expensive. So here and we choose and the representing and the 0D autoignition process to construct this and active directions. Okay, so this is what we're showing here. Okay, and by performing manual and autoignition simulations, we identified and the active directions. The reason why we can do this is for this frame, we know that and this frame is governed by this autoignition process. So that's why we can use this 0D and autoignition process to identify. Okay. Once we have this active direction, and we can performing samples only in this 1D and active direction, and we can obtain this PDF and of this lift of height. Now, and it's a CFD simulation, and you are no longer have only one and single point prediction. Now you have a PDF distribution. Also, and more important than that, and what we can do is we can examine and the leading components of this active direction. And what we notice is actually, and we can identify and the governing and elementary reaction for this lift of height. And what we notice is that for this particular frame, and the key elemental reaction governing and this lifting of height is and these three ones. Okay. Now that's what we did and for propagating kinetic and uncertainty in the flame simulation. And more recently, and we demonstrate and how we can propagating and the kinetic, physical, and uncertainty and in the flame simulations. And so this is the example we are considering. Okay, so suppose we have this and barrels and Kirchhoff and supersonic and water jet flame. So essentially, the fuel is coming out from this. The fuel is coming out from this and the jet. Okay, so surrounding is and high temperature and air. And for this flame, and we are interested in two things. So quantity of interest is the lift of height and the flame over distance. Okay. And the uncertainty and the parameters we consider are the 21 uncertainty kinetic rate constant. Okay, so this is a kinetic uncertainty. So for hydrogen flame, you have this 21 elementary reactions. Okay. And in addition to that, and we also want to consider and the turbulence and combustion model parameters as well as uncertainty in boundary conditions. For example, we consider and the K omega SST model constant beta star, and also and the turbulent Schmidt number, turbulent Planck number, and PASR combustion model constant, and the normalized fuel inject pressure, and also the airstream and the static temperature. Okay, and this is a nominal value we are taking, and for this model parameter, and this is a range. Okay, and we assume a uniform distribution for these parameters. Okay, and for the kinetic uncertainties, and we assume a normalized the log normal distribution. Oh, the strategy we are taking is essentially and it falls into two tiers of reduction. So the first tier reduction is okay. For the kinetic parameters, we use the represent and 0D and 1D and Autoignition and flame simulations. We identify this is 1D important directions in the kinetic rate constants. Okay, so now you reduce from 21 to 1. Okay, for chemical kinetics. Then we combine this 1 and active direction for chemical kinetics with turbulence combustion model parameters. Okay, then now and we do a second and active subspace and reduction, and we reduce to a lower, and here once again a 1D and active subspace. Okay, so now we lump and 1 plus and 6 or 7 primes into and finally a 1 and active direction. Okay, then we use the response surface and together with Monte Carlo and sampling and eventually we get as a PDFs of the quantity of interest, and in this case, it's the liftoff height and the flame wall distance. Now here is what it looks like. Okay, now for flame liftoff length, and what you can see is if you look at and the components of this active direction, okay, you will see the large contribution from this and the reaction, chemical reaction, and also and the contribution from the terminal prime number. Okay, so this actually and this is quite informative, and considering and the flame is governed by the autoignition process. So you have fuel mixed with hot air and get autoignited, and the flame is stabilized and initiated and stabilized. Okay, so that's no wonder why and the liftoff height and is very sensitive to and the chemokinetics. Okay, so as you can see, as the active subspace method can identify and the controlling and the physiochemical process. Okay, in contrast, you know, for the flame wall distance, if you look at the components of the active directions, now the leading and a factor is and the turbulence model parameter like beta star and also the Schmidt number. Okay, and this is also understandable considering and the peak temperature. Okay, as long as the flame is formed, the peak temperature is determined essentially by the location of the stoichiometric mixture fraction. Okay, that is governed only by and the mixing process. Okay, so that's no wonder it is affected by and the turbulent model parameter as well as the Schmidt number and the most. Okay, so as you can see, and the active space and can identify and the individual controlling a mechanism for and in this case for the liftoff length and the flame wall distance. Okay, more interestingly, and here and we use and the flame wall distance as example. So essentially, and we will consider the quantity of interest as as a different so flame wall distance at different downstream location. Okay, as quantity of interest, you will see and starting from the flame initiation, flame stabilization. If you and following as a downstream direction and the influence, okay, and of the turbulence modeling and get stronger. So essentially, what it happens is the flame and particularly for this and flame wall distance is starting, and the governing process initially is controlled by and chemical reactions. So that's how it determines the flame flame initialization and stabilization, right? And gradually, and is a switch to and is a controlling process by and turbulent mixing. Okay, so active subspace method and can show you the spatial evolution of the and the controlling process throughout the flame. Okay, so in addition to revealing and the controlling and the phenomena, and the active subspace and the UQ by active subspace method can quantify and the predictions, right? So here is a PDF of the liftoff height, and here is a PDF of the flame wall distance. So if you look at the PDF distributions, okay, and if you only consider and the boundary condition uncertainty, okay, and its PDF distribution is quite narrow, okay, so the uncertainties in the prediction and with respect to the uncertainty in the boundary condition is actually and the influence is small, okay, and here is the influence of physical models, okay, and here is the influence of the chemokinetics uncertainty. So as you can see, and the dominant and the uncertainty and in the prediction of liftoff height is coming from and the source of and the chemokinetics, okay, essentially the green and the curve. And in contrast, and for the uncertainty in the flame wall distance, and the dominant contribution is from the physical model. Okay. So that's pretty much, and I want to share with you and the progress we made for transfer PDA method. So hopefully, and get your flavor and for the PDA modeling, and we have come up with a zone adaptive modeling framework, and also for mixing models, and we come up with a new kernel constrainer mixing model. It can account for localness in composition space, while at the same time is efficient. And also we have done certain work on modeling and the relative scalar and mixing time scale. And so new hybrid model we come up with can recover the correct and frame and the block zone regime limits. And also we attempt to quantify the uncertainties and physiochemical and parameters and propagate them and in the safety simulations. And we show that as a low-dimensional active subspace exists in kinetic uncertainty, and we can quantify the physiochemical uncertainty through the successful dimension induction by active subspace. And also the active subspace method is quite informative in terms of, and it can give you information on the controlling and physiochemical process in the turbulent frames. And so last, and I want to thanks my collaborators and contributors and for all this work. There are Dave and Steve at Cornell and my current team from at UConn and Jackie and Sandia and Evan Hawks at University of New South Wales, Yusuf and Olivia at MIT, and also my the group at Tsinghua. And that's all. And thanks for your attention. And we're most happy to answer some questions. Yeah.
Thanks, Professor Ren, for this very, very impressive talk. I believe everyone agree with that. So we have a bunch of questions. Let's go over them. Actually, many of them from myself. Hope won't occupy too much time. So first question from me. So I noticed you have a nice figure in early slides. One show that the reaction zone length scale is smaller than LES grid, but the chemical time scale can span the whole range, including even the Rand's time scale. So I try to see your comments on this very different observation. Has any special implication on the modeling?
So here is just as a schematic and showing as a wide range of length and chemical time scales. So for the length scale and for the flame thickness and particularly and for premix flame and very often and it's true and the reaction zone is much smaller and than and even for the turbulent and chromatograph scales. Okay, and in terms of a time scale, and here I draw a wide and a range of chemical time scales. Okay, here is okay, and for chemical reactions, and some are really fast, and once two molecules collide and they react, so those chemical reactions are really fast. And in practical applications, and we do have certain chemical reaction processes are quite slow, actually, like the NOx formation. Okay, and it occurs at scale of millisecond, and that's compare even larger, and that's comparable and to the typical residence time, and that's the reason why I draw and and this is a wide range of scales.
Okay, very nice. So the next one is can you talk a little bit about the coupling between transport PDF and multi-phase models like for soot and spray, because especially if both use the particle method?
Yeah. So that's a very nice question. So in the spray and flame simulations, so essentially, if we use the transfer PDF for the gases phase, we do have this Lagrangian, and and distribution. So what we did is okay, you maintain two sets of Lagrangian and and tracker, and one for the fluid and the droplet, and one for the gases and particles. And we do have the interaction, and essentially it's mass and enthalpy energy and exchange and at a subgrade or subgrade level. So essentially, when the evaporation and occurs, so it will release a certain amount of mass as well as the energy, and a certain amount of mass and energy will be distribute over the gas phase and the TPDF particles, and according to certain laws. So for that part and for the mass and energy coupling, and the people also come up with different algorithms like the rapid mixing, or and the nearest neighboring approach, etc. Yeah.
Okay, thank you. Very nice. So next question is from Professor Jay Guo. So why focus on piloted premix, non-premix, and partial premix flame? I think the pilot is very limiting to practical application like gas turbine combustor, where the flame stabilization is by multiple swirling flows.
Yeah.
I think you read the question very well. So I'm interested in hearing Professor Ren's comments. Yeah.
So actually, thanks, Professor Go. Yeah, you are right. And what I'm showing on this presentation, and most cases are from the jet flame or star Bunsen flames, etc. And you are right. And for practical applications, and some more relevant case are the swirling and multi-swirling cases. And actually, if you look at a certain PDF transfer PDF simulations, and people have already working on these swirling flame simulations, like I'm showing here, and done by Azari and Givi, and back in 2015. And also actually within my own group, and the result I don't show here is we also using the adaptive and zoom model approach, and for certain model combustors. And for that one, it is also swirling flame, and the results are quite promising. Yeah.
The next one comes from myself again. Can you show us the criteria for your adaptation method and comment on the sensitivity of it? Also, I guess the coupling between this adaptive TPDF with dynamic adaptive chemistry might provide a good performance.
Here, and I only show a very few results, and we got within this past 2 years. So okay, so as I illustrated here, and the PDF zone are dynamic determined, and right now we try and we use two different scenario criteria. One is based on the local and Dunker number. As long as the turbulent chemistry interaction and is intense, and judged from the local and Dunker number, and we will use the TPDF method. Okay, so as you can imagine, and the TPDF zone will be dynamically changing. Okay, and during the static simulation, particularly on LES, this LES context. Okay, so that's the criteria one criteria we tried. And we also tried the criteria like, and for non-premix flame, you can also set the criteria essentially based on the reactivity, that is based on the mixture fraction. So you can also do that. So the point is, okay, in this dynamic framework, and the criteria for PDF zone is user specified, and it can specify and based on a certain physical and quantity like Dunker number, mixture fraction, etc. Okay. And so that's how we handle the submodels, how to assign the submodels. In terms of the coupling, so as I mentioned, it's a base model, and we have demonstrated for this case, and we use essentially one-step mechanism, and for laminar flow rate model, so no TCI and interaction. Okay, and so you can imagine. And we see this flame zone, and the prediction in temperature is totally not wrong. It's total and far away from the accurate one. Okay, and in this region we use the detail mechanism. Okay, so here we have two sets of consistency, And one consistency is within this PDF zone. Okay, the predictions of the base model should be compatible with the predictions from the trans-PDF method. Since in this region you have duplicate representations. The base model, for example, base model also has a methane, oxygen, CO2, water information, right? The trans-PDF model also can predict CH4 and oxygen, etc. So the two sets of mass fractions should be consistent. So the method we did is we use a relaxation method. We will relax and the base model solution towards and the trans-PDF model solution within these PDF zones. So that's one set of one level of consistency. That's how we achieve use a relaxation method. The second level of consistency actually is the maximum consistency. So in the base model, and for the base model, you only have very, very few species. And for the PDF zones, you have a whole bunch of species because you use the detailed mechanisms. So how do you represent as the species? Essentially, how do you reconstruct this species information that is not available in the base model, but should be is needed in the TPDF model? So essentially, here we use like constraint equilibrium, constraint chemical equilibrium assumption to reconstruct as radical information as a model interface. So that's how we did and these two level of consistency. Yeah.
So also, do you do a loading balance here for parallel computing? Because
that's right. That's right. Okay. So for parallel and loading efficiency and parallel computing efficiency, we use software we developed before, like X2MPI. So during the chemistry step, particularly for the trans-PDF zooms, and we rebalance the particle and chemistry integration among and all the CPU and processors. Okay, so by doing that, and we speed up the calculations. Yeah.
Okay, great, thank you. The next one from Professor Jago again. What is the difference between the Monte Carlo mixing and the stochastic mixing that the later Jerry Fitz and his student have utilized for many decades, starting with the spray simulation?
Actually, I also see on the chat board a related question to Professor Jago. So what's your opinion about the Eurasian stochastic field method? And these are the two related questions. Yeah. And I'm really sorry, I'm due to a time and constraint, and I did not talk about the Eurasian and PDF approach, Eurasian stochastic field method or Eurasian PDF method. Okay? And as you both of you mentioned, in addition to the Monte Carlo and implementation, and people also come up with Eurasian as well as Eurasian field and stochastic field and representations for TPDF method. Okay, and each of them make big progress and actually recently. So we do see publications and for twin flame simulation using Eurasian stochastic field method as well as Eurasian PDF method. Okay, I think that. And for the mixing models and in my understanding, okay, maybe not right. Okay, I didn't do the Eurasian or stochastic field method very much. So in terms of mixing model, and for the Eurasian and field and stochastic field method, the mixing is kind of more kind of mixing different amongst the different fields. Okay. And even and like the IEM model, it shares very similar formula and with with the version and with the Monte Carlo and IEM and implementation. But as the underlying physics is quite different, and since I did not do much on the Eurasian and trans-PDF Eurasian and stochastic field method very often. So I don't want to comment here. Maybe I didn't fully figure out the subtle difference and at this stage yet.
Actually, Professor Jacob have a bunch of questions here. So I think the next one is, could this not be done much more accurately by considering the joint temporal and spatial probability density function and limiting the time scale and spatial scale for localizing the model?
So if you want to localize the simulation, could you do that by considering time scale and spatial length scales so that the correlation between realization decreases as the distance increases and as the time increases, all the time satisfying the length and time scales?
That's actually a very good suggestion and a very good question. Yeah, that's right. And so if somehow we can model, or if we know the local and flow and time scale, or the length scale, and if we can somehow build some part of those information is models, and actually they should resolve some issues I mentioned here, and the localness issue. Yeah, actually, and this is what people have done and tried to do in mixing model and business, like the shadow particle position method, or also the MMC method. They all somehow borrow or come up with certain length scale information and from the flow field. Yeah.
Another question from Professor Jacob is, do you believe more in DNS data or in experimental data? Are experiments still necessary if DNS data can be trusted?
Yeah, I thought I might entertain you a little bit by asking that question.
No, actually, at least from my perspective, okay, and when I collaborate with my colleagues and working on some model development, I appreciate every effort as they made in and either in DNS and the simulation or experimental and measurement. So more data suppose they can provide us the detailed information, and it will become more helpful for our model development. So that's my comment. Yeah.
Okay, thank you so much.
Your hybrid mixing timescale model seems can also be extended to generate a new PISR model. So try to seek your comments on that. So I think you use for the transport PDF, but I believe can also be.
Yes, that's right. Yes, that's right. So right now the hybrid mix model only works for premix frame, and recently we also want to extend to the Kernel and frame, including the partial premix frame, and also the way and how it and constructs as a particular as a contribution from the frame structures. I think it will also have certain hint for the time scale parameters in the other combustion model, like the one you mentioned, PSR. Yeah, and it will be really interesting looking into that. Yeah.
Yeah, because the form looks very relevant. Yeah.
Yeah.
Okay. Yeah, we finally have a question not from myself or Professor Jacob. Yeah, this is from Zhaoping Yin. So one question comes from the comparison between LFR, FDR, and other models. I will read a paper comes from your group with the title Structural Analysis and Regime Diagram of Laminar Counterflow Spray Flame with Low Temperature Chemistry, in which multiple flame structures are found under the same initial and boundary condition. I'm wondering how you use LFR model. Does this multiple laminar flame structure have influence on the LFR model if you choose either one structure of them?
Thanks. So the paper you mentioned is for the direct spray flame, and in that paper and we essentially simulate and certain laminar and count flow configuration, and with a direct spray, to investigate the potential and flame regime, and you will run into. So this is a centralized and high temperature flame or bimodal and flame, etc. Okay, and so that's what we did and for that paper. And what we found out is according to the different and essential inflow parameters, and you may run into multiple regime and situation. And but in terms of so turbulent combustion model, like I mentioned here, LFR, laminar final rate model. Here is the base model. Why we choose it is this is start point, okay. And from the modeling perspective, an LFR is applicable to any flame configuration. Even so, it may not be accurate, okay. So that's so for the base model we can use different other models like EBO, etc. Doesn't matter, and second frame model doesn't matter. And so that's the reason why we only use it as a base model for the region. Why it may break down, and we will come back to the high fidelity model like the transport method itself. Okay, so that's the kind of philosophy we have here. So the base model. And we only look for a general model applicable to different configuration and may not be accurate for certain region. And we use a high fidelity model and to patch those regions. Okay.
Thanks, Professor Ren. Hopefully to see you in the future.
Bye-bye. Yeah, have a good night.